Thank you both. All right, for our next talk in the geothermal realm, our next speaker, Eric Chevrier, could not make it today, so I'm going to invite Don Ford, star of the day, to deliver his talk on his behalf.
Thank you. I'll do my best, and Eric sends his regrets. For those of you who aren't aware, TRCA for the last number of years, seems like lots of them, has been in the process of rebuilding our head office at 5 Shoreham Drive. We've relocated temporarily to 101 Exchange, just at the west end of the parking lot for IKEA and Vaughan, if you're ever looking for us. So with this new office, the idea was to make it a very green building, obviously representing the mission, goals, and objectives of TRCA, that we wanted to make sure it was energy efficient. It's actually a wood building, even though it's multi-story. Everything above grade is wood, including the elevator shaft, as I found out. Special permission and lined with double layers of gyprock, but it passed fire code. So we're going to talk a little bit about the system design, some of the hiccups we had along the way, our drilling experience, because it was kind of interesting, and some of the lessons learned along the way, because there were a few. So we really wanted to set a benchmark in sustainable design overall for this building. And sorry, I don't have any current pictures that do it justice, because they're still finishing the cladding as we speak. Some of the sustainable features include rooftop solar thermal, rainwater harvesting to irrigate the green roof, interior waterfalls for reducing energy and improving indoor air quality. They're actually connected to the air handling system, which is rather unusual. So I wondered what they were. I thought they were stairs, but it's actually, they have stainless steel panels and the water drips down through those, and it's used to maintain humidity in the building. Electric vehicle charging, the solar chimneys for some passive heating and cooling, and of course, for the topic of today, the open loop geothermal system. This is one of the few, I'm not going to say it's the only open loop system commercially in Ontario, but it's certainly one of the few. And then, as I mentioned, mass timber construction. So what we were targeting for this was LEED Platinum certification, the Tier 2 for the Toronto Green Building Standard, and also the Canadian Green Building Council Zero Carbon Building. So why geothermal? Well, it's one of the most effective ways of heating and cooling a building, especially when you involve either open loop or closed loop systems. I'm not an economist, I'm not an engineer, I'm a geoscientist, but the numbers are astounding in terms of the energy savings you get from using constant temperature groundwater or ground cooled and heated system. And you think, well, there's not a lot of difference, but in winter, even in Toronto, it goes down sometimes, some winters, maybe not today, minus 15, minus 20. The groundwater temperature is pretty steady at 10. So you can actually extract heat energy even in the winter. But the idea of using the open loop is that we can pull from the ground at that constant temperature. We even looked at switching between wells, so you can for optimization, you can actually store the thermal energy. In the winter, you put it through the heat exchanger and it cools down the water. You put it down the cold well, and then in the summer you draw it out of the cold well for your cooling. So unfortunately, we didn't have quite enough infrastructure for that. We went with a straight open loop with one injection and one withdrawal well. We felt this was the most reliable and partly how things went in building the building, because certainly one of the things we learned, if you're going to do this, do your hydro-G work first. And here's the geologist telling you that, but unfortunately, others were involved in the initial planning, and the initial thought was closed loop, so they retained a different contractor and then asked me a year later what I thought. So this can be a very cost-effective solution. Obviously, the more efficiently you drill your wells, the better. And one of the outcomes of this project, we're trying to map out some of the areas in Toronto that are probably more conducive to open loop or also closed loop, so someone doesn't waste a lot of time trying to find water when there isn't water to be had. So some of the design considerations, we put together the information from geologic maps, as imperfect as they are, as we found out. That then leads to test drilling and looking at how deep the overburden is, what sort of bedrock do you have. The bedrock is usually pretty well determined, but the overburden is quite variable. Some of the hydrogeologic conditions, you have aquifer maps, we have a lot of those, and it is under our head office, so we hope we have a good map. As it turns out, we did not. Sometimes the bedrock valleys aren't exactly where we thought they were or should be. And some of the hydrogeologic characterization, because flow gradients, flow rates in the groundwater system can affect the functioning of especially an open loop system. And then there's the energy characteristics. So we have the earth temperature, how deep are you, where's the best aquifer, or are you going deeper into the closed loop systems. And in situ thermal conductivity testing, especially for closed loop systems. Soil and rock have different thermal properties, as you heard in the temperature talk. And there's thermal diffusivity as well, and also aquifer effects. So if you think you've got a nice stable temperature and you've got a really good aquifer system coming right through where your closed loop system is, it can affect the performance. So what are the main options? Closed loop, as I've talked about, they can be horizontal. Sometimes they even put them in lakes, although we kind of discourage that. Borehole loops are becoming common, and that's what was initially anticipated for our head office. And I might add, they did proceed based on the knowledge that we had at the time, that we didn't think we had a bedrock valley under our office. We knew it was close. We thought it was a little further west, and that turned out to be wrong. Open loop, you have water wells, and you need, one of the key things is it's not too hard getting the water out of the ground. It's often more difficult putting it back, especially if your water level in your well is close to ground surface. You're going to have a hard time getting it back into the ground without ending up with water on ground surface. And then you can have a standing column well, and that's if you have deep unfractured bedrock, which isn't the case. We've got the Georgian Bay Shale, which the fractures are closed at depth, but it's still pretty messed up rock. So our design phase, as I mentioned, we thought closed loop at first, or at least the designers did. And for this system, you put water or heat transfer fluid circulated through the closed loop system, plastic pipes into the ground. They're sealed, hopefully. And then you hook up the building HVAC, and it's simply the heat pump, and that's where I say I'm not an engineer, but essentially extracts the heat energy or cold energy out of the transfer fluid and heats and cools your building. So on you go to drilling. So we did that. So we thought shallow overburden at the site, and there was a nearby borehole that was terminated about, I guess, 20 meters below grade. So we thought, well, or at least they did. So they started with a very deep well, or sorry, a deep borehole. Went about, and sorry, I'm going to switch over, 200 meters into bedrock, and they found 3 different aquifers. Only problem was they only logged from chips, and they were a closed loop type contractor, not really trained in how to log chips or whatever. So their logs were somewhat different from reality. And sometimes it can be interesting when you find that geologic conditions are not what you expected. So they then asked for my opinion. The closed loop contractor said, well, we identified 3 really nice aquifers. You got your pick. You better go that way. Well, one of the problems was that the building construction was already underway. It's really hard working around a construction site when you're trying to drill the well that you need for that building that's under construction. So why did we want to try open loop? Well, first of all, you only have 2 wells, and in our case anyway. And from my perspective as a geoscientist, you're using a more reliable form of access to the subsurface, if you will. That the well has to pass Reg 903. It has to be constructed by a licensed water well contractor and technician. And so there's a lot more documentation and assuredness that the well has been properly constructed, as opposed to a closed loop system, which they're put in fairly quickly and sealed with bentonite, and they're very deep, and there are a lot of holes, so they can represent transport pathways into the subsurface. So the open loop I prefer for environmental reasons, but also the groundwater is a great way of you can actually move the groundwater around with typical groundwater pumps, put it through your system, and you're not introducing a heat transfer liquid into the subsurface if a pipe should break. And you can have one single high capacity well. In our case, we ended up with 150 gallons a minute. So that one well could have replaced essentially tens to potentially hundreds of boreholes for a closed loop system. So, and our site is very small. For those of you who have been to our head office, it's not a big piece of property, and it now has a rather large building on top of it. So that's kind of what the schematic looks like. The idea is that you pull from a supply well and put into the injection well. I mentioned there is something called aquifer thermal energy storage, where you can actually switch those, but that requires extra pumps and extra controls. So is perhaps more feasible for a larger structure or complex. So we started the drilling in 2020. Here we are 2024 and the building's still not ready. That's okay. The geothermal system's ready. And we found bedrock at 125 meters above or below ground surface. So a long way from the 20 meters from the nearby borehole that was put in. We found that the 3 aquifers identified by the initial drilling really turned out to be 2 that were of any quality. The 2 shallow ones weren't either conductive enough or thick enough. A lot of interbedded sands and silts. And it doesn't take much to drop the hydraulic conductivity. So we found this contact aquifer in the bedrock valley and really good formation. The problem was it was deep. That increases your well costs. So we drilled a second well. The first well was PQ cored. So we had a good stratigraphy control, but unfortunately it wasn't big enough to really pump it at 150 gallons a minute. Can't get a pump that big down that small a well. So we drilled a second well and it only made 75 gallons a minute, barely. In fact, we ran it dry. And then we thought, uh-oh. One good well, one bad well on the same site. So we needed 150 gallons a minute, that was our target. And just a slight change, as you know, in hydraulic conductivity, it doesn't take much. And pretty soon you don't have enough water. So went out on a limb. Still employed by TRCA, fortunately. And we put in a third well. Third well was the charm. It actually pumped better than, well, it made over 150 gallons a minute quite easily. So now we had 2 locations that were confirmed as high quality aquifers. We just didn't know exactly how much the third well. So we had to then go back to the very first location and drill a third well. So it could have been done much more efficiently in our case had we conceived of an open loop system from the start. But even then, we think it's saved money over the implementation costs of the tens of boreholes that would have been required down to, say, 200 meters for a closed loop system. That just shows you some of the flow gradients. We did map those out looking. What you want to make sure is that you don't end up messing up the chemistry or the temperature of your other wells. So we were fortunate that they were cross gradient. You can see the third well that doesn't say very well, 290 up at the top. This was the well that didn't produce water. These two, each of them will produce 150, 200 gallons a minute without difficulty. And that's what it kind of looks like. We had the really deep hole all the way down into bedrock, and then the much shallower wells that are required for the geothermal system. And something else you have to watch out for, of course, is quality, especially when you're working with an open loop system. You don't want to plug up your screens. You want to watch your velocities. So you have to try and keep your water velocities in the screen down below a certain threshold. And then as well with injection, you want to make sure that you can put the water back in without it backing up into the system. So our temperature again was around 10 degrees, so that worked out well. The chemistry worked out favorably. And the nice thing is it's non-contact. It just passes through the heat exchanger, doesn't contact anything along the way. The thing is you still need a certificate of approval, or mind escapes me now, the new term, for this as a waste system, because you're putting the water back in the ground, even though it was the water you took out from the well 75 meters away. So we looked at some rough costs for the closed loop system versus the total, and the closed loop system came in at about 1.3 million in the end, and the open loop was 872,000, give or take. So it was still cheaper, even though we didn't maybe do it in the most efficient way possible. It shows you that it can be a very efficient and cost-effective technology. So some of the lessons learned. Yeah, here's the hydrogeologist saying, do the hydrogeology study early. Yeah, talk to your colleagues sometimes. Monitoring of an open loop performance, you need to make sure you monitor it to make sure that the chemistry is okay and you're not messing up your screens and requiring premature maintenance on it. And you have to watch out for changes in the specific capacity or pressure drops if you've got some problems with your well screens. And you still may need some redundancy in your HVAC system. Not a huge deal. I will say that the HVAC system was much simpler with the open loop system than it was with the closed loop. Opportunities, we think there are a lot more opportunities for open loop systems than I'll say the GTA in general. We know that there's a Laurentian channel. One goes down the Humber, another channel down the Don. So we know we have these bedrock aquifers, or sorry, bedrock valleys that produce very large quantities of high quality water. And it says vast distribution of aquifers. They're somewhat limited because they're channels primarily, but they are right through the key parts of Toronto and also north of Toronto. And we believe that the open loop systems do have the potentially to help offset some of our increased energy needs. And we're seeing this as well, that they've introduced deep water cooling now, and they've just put in a new intake for Toronto using lake cooling in a similar way that we're using geothermal in the office. And moving forward, we're working with funding from a variety of agencies to prepare some maps on terms of aquifer resources, trying to refine the bedrock valley locations. One of the things is people stop at the first aquifer typically, so they don't necessarily go down to bedrock, and that's one of our challenges in mapping out these valleys. I'm a big proponent of gravity that's been done by the OGS. I think it can be used even in urban settings. And And I think we need to make better use of some of the data we get on geotechnical and hydrogeological reports that come into the agencies to expand our knowledge. And also get that information back in. We make extensive use of the Oak Ridges Moraine Groundwater Program data set, and we have Steve Hollish in the back and Rick Gerber and others from the team here in the room today. And using systems, data systems like that to better understand your aquifers and aquatards really can help you refine what form of geothermal heating and cooling will work best for you. Thank you.
Thanks, Don. Do we have any questions? Maybe one? Oh, here comes Steve with the mic.
Uh-oh, it's Chris. It's going to be a tough one.
I have two quick questions. The first is, I didn't see in the budget, I didn't see any groundwater modeling. Where was that?
Because we didn't do any.
Joking aside, I've been working with Brian Beattie on these, and we're up to model number 5 in this area. The other question that I had is, the proof will be in the pudding, and so what exactly do you plan to monitor?
Some of the things they're monitoring are temperature in the system, chemistry, making sure that we're not screwing up the chemistry, because as you know, even though everything is supposed to be tightly sealed, you're not introducing oxygen, you're changing temperature, which can do some things with solubility. So look, making sure that monitoring of wells, we're keeping the one monitoring well to look at the aquifer level, because technically if we're putting back in the same amount we're taking out, there should be no net effect, but they're not in the same place. So we have to make sure that over time we don't draw down the extraction well too much or raise the other one. Either one would point to perhaps loss of efficiency in the well. Oh. It just helps the people online here, so that otherwise they have no idea what the question is. Might be easier for my answer.
Yeah, I wonder, the injection well, was it one of the 3 you presented, or is this well in a different location?
Well, the third well essentially went, they're in a triangle. The third well, the third production well, if you will, went where the first PQ well was. It's only a 3-inch well. So again, we couldn't pump that or inject into it. It's too small diameter. We need at least 6 and like a standard water well, 6 5/8.
What's the separation between the wells, the injection well and the production well? The distance between the wells?
I believe it's about 75 meters. Not huge.
Any idea by when a shortcut will be generated between
well,
the wells in terms of heat transfer?
Yeah, because we're not expecting a lot of heat transfer breakthrough, the combination of the relatively low temperature change to the water, it doesn't change dramatically the temperature of the water, and the fact that they're cross gradient, the flow is actually away from both wells. So it'll go down into the valley, the thermal plume, if you will, from both wells. One will get colder, one will get warmer, but probably only by about, I would say, 2 to 4 degrees.
And what's the extent of the area of influence of those plumes?
We're not sure, because we're in a natural area beside the Humber River Valley in this location. We're keeping all the wells that were drilled and trying to make use of them as monitoring wells. So we can I'll have more information once the building gets occupied, which is hopefully Q2 this year.
Did the construction of the injection well differ from the production well?
No, they're essentially the same. They were done by the same contractor, same diameter, into the same aquifer.
Thank you.
That's another point. For open loop, you want to try and make sure that you put the water back in the same aquifer you got it from, so you don't mess up the aquifer, natural aquifer chemistry.
Okay, we'll take one more question here and then we'll move on to our next talk.
Hi, Don. Yeah, so there is a big difference on the initial cost of the construction, like $500,000. In terms of maintenance, have you figured which one is more expensive to maintain?
It's a trade-off between the maintenance. The maintenance is going to be higher with the wells because you have to perhaps rehab them periodically. Whereas a closed loop, you're looking at total replacement if something fails. So it's, what's the probability of failure? It's polyethylene pipe. We know that pipes fail on occasion, but it's really hard to predict when that occurs. The thing is, if it happens with your closed loop system, you're going to have to, your costs are much greater because you have to pull everything out and reconnect everything underground. Whereas with a well, you simply replace the well if all else fails. And now that we know exactly how deep it has to go, we don't have to fiddle around with actually where or how deep.